One of my favorite things about separations is that it really displays what the concept of a trade-off means. So we saw this in distillation a little bit with the trade-off between n, the number of stages, and the reflux ratio R. There's a similar trade-off in absorption and stripping, but instead of the reflux ratio, it is the solvent flow rate. So for the example problem that I've solved in the last couple of videos, remember that my final answers were for n is equal to 1 stage, my solvent flow rate for L was 1450, I think it was. Let me go back and check. Yep, 1450 kmol per hour. And in the last video I showed you that for n is equal to 3 stages, L drops down to, and it is less than 150 kmols per hour. So just like in distillation, the number of stages has an inverse relationship with the solvent flow rate. So as n increases, the needed solvent flow rate decreases, and vice versa. And you can imagine how we can have the same discussion about operating costs versus capital costs, where capital costs are the one-time upfront cost of the equipment, which scales by n. So as many stages as you have, that is going to increase the amount of money that you have to pay for the column for the first time, while the operating costs are set by the amount of solvent that you have to feed to the column. So if you decide to go low stages, you need a lot of solvent flow rate. If you decide to increase the number of stages, you need much less solvent flow rate. You can really draw an application here to cleaning the dishes after dinner. If you say you have a big pot that's full of spaghetti sauce or something, the more times that you wash your pot, the less water that you need. So I see that all the time when I'm doing my dishes, and it makes me think of this class. So given that, a logical question to ask then would be the same question that I asked in distillation, which is what are the limits of operation? Because once we establish what the limit of the operation is, then we can go in and start to try different things and find the optimal solution. So remember that for a given separation process, typically your boss is not going to tell you anything other than what you're starting with and what the desired finished product is going to look like. And there are many different combinations of n and solvent flow rate that will achieve this given goal. So unlike for distillation, where sometimes n min was greater than 1, for absorption and stripping, n min is always equal to 1. And this, of course, assumes that if solvent flow rate is high enough. So I'll just draw you a quick graph to display this. So when you start off with drawing your plot, once again, you always know what your equilibrium data is going to look like, always going to be linear. And no matter what your y in and your y out specified are, you can always do it in one stage. So let's do the same thing where, let's see, we did this example already, but if L goes up, as L goes up, the slope of the operating line is L over V. So as L goes up, then L over V is going to increase. So at its limit, if I send a lot of stuff, I could end up with an operating line that looks like that. You can see that even in one stage, I can get pretty far. So even if I don't get all the way out to my desired Y out, I would just have to try again with a different operating line. So let's say I really push the limit as L goes up by a lot. Then in one single stage, as I've shown you in this little cartoon, you can reach Y out with any number of stages, with one stage if you want to, if your L is high enough. That's not really an interesting case, though. This is good for kind of figuring out what L max is or what V max would be for a stripping column. Remember again that if you're questioning why, if I'm doing a stripping column, if V goes to infinity now, my slope would go to 0. And in that case, remember that my operating line would be below my equilibrium data. But I'm talking about an absorber here where L is increasing, right? So this is corresponding to V max or L max. All right, that's one limit. The other limit that we might want to figure out is what is the minimum solvent flow rate that we have to send. And this is actually the more interesting one. So this is what I'm talking about with the limit. What is the minimum amount of solvent that I need to send? And this is an interesting question because just like you hopefully saw in distillation, that the overall cost of an equipment is going to be dominated by the operating costs. In general, it costs much more money to keep a piece of equipment operated in terms of energy, in terms of recurring costs, than it does to build it for the first time. So typically in industry, what you want to do is prioritize those operating costs. And to that end, it may be beneficial for you to minimize the amount of solvent and increase the number of stages. So this is why it's really helpful to know what the minimum amount of solvent you need. And this is going to correspond to, remember again, that as solvent decreases, N is going to increase. Corresponds to N is tending towards infinity. Now, what does a column with an infinite number of stages look like? First of all, it's not a actual construct. This is just a thought experiment to design what the minimum amount of solvent is, just so that you can establish what your design space even is. So once again, let's start with an equilibrium data, and we'll assume that the bounds of our axes are adjusted such that the slope of the operating line is about 45 degrees. It doesn't mean that the slope is 1. It just means that I'm adjusting the bounds of the axis to make it look like it's 1. And let's say I start with a given y in and I have a given y out. So if I start drawing operating lines, and I've played around with drawing lines with OneNote and it doesn't really work. So I'm just going to do my best with drawing lines by hand. I can start putting in all these operating lines, right? Let's say that all these operating lines are potential L's, right? So as L is decreasing, the slope of my line is also decreasing because again, the slope of the line is L over V. Well, by doing this experiment, it should become clear that below a certain amount of flow rate, I'm going to have a operating line at which it's not even possible to get 2y out. So let's take, for example, let's erase the other 3 lines and say that this was my operating line. And it wouldn't make much sense because it's crossing over the equilibrium line. And you should realize that for a majority of those operating lines, unless I'm parallel or something, you're always going to intersect the equilibrium curve. It just might happen outside of the bounds of the plot. So what would happen here? If I started stepping stages off this line, I'd say 1 stage, 2 stage, 3, 4, 5, 6, 7. I wouldn't stop there. You could actually, if I zoomed into this, kept zooming in and kept drawing stages, you would see that even if I had infinite stages here, they wouldn't be doing much, first of all, but I could never get past this. This is called, again, the pinch point. Right, so if my solvent flow rate is low enough such that I intersect the equilibrium data before I reach y out, remember that this y end, we'll call it, is less than y out. We're not reaching the desired specifications. So we're going to have to increase the solvent flow rate a little bit. Okay, so what does that look like? Well, if I make it such that I know that I'm going to have a pinch point somewhere, and I want the minimum amount of solvent that is still going to theoretically reach my limits, let's say that I specify that my pinch point is going to occur there. Well, if I know that my pinch point occurs there, then I know a point that's on the operating line, and I know a point that's on the operating line down there. I can connect those 2 points. And then I know that if I start stepping off of this line, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, all the way up to infinity, at least I am now getting to my specified y out. And I can figure out what the minimum solvent flow rate is by calculating what the slope of that line is, and I'd know what V, the vapor flow rate, would be, so therefore I could calculate what L min is. So that's all I want to say about establishing the design limits of L min and N min. And once again, I'll just mention briefly that stripping would be the exact same, just the opposite, where the operating line would be below the equilibrium curve, and we'd still be talking about V min. Just in this case, the operating line would be getting steeper and steeper until we reach the pinch point. That is all for this video. Thanks for watching.